Welcome to the session. In this session, we take a look at how to compute a linear regression model with SPSS. So let's start. Here I'm writing SPSS. It's a dataset about football players. Each football or soccer player has a row displaying different attributes. For example, the first soccer player in the row is Ter Stegen and the name as a property is recorded. Furthermore, we have information about age, height, weight, club, and so forth. In the first example, we take a look at the relationship between height and weight of soccer players. But before we start to model the relationship, we do some descriptive statistics. One way to do it is to visualize a variable. So let's start. I will do this first for height by using a box plot. So I click on Graphs, Chart Builder, and then I select the box plot and I want a single box plot, so I just drag and drop the 1D box plot and select the height variable onto the x-axis. What I can do now is to do further customization. I will just delete the title because it does not add much information, and this is all the setup to produce the box plot. I click OK and now I'm in the result viewer, and here I see the box plot of the height variable. We see that the median is around 185 and that the mid 50% lie around 179 to 188. So the box plot provides us with a good overview. Now I visualize the second variable we consider, weight, and I use the histogram just to show you some variation. So I click on Graphs, Chart Builder. I reset this menu and now I select histogram, just a simple histogram because we're just visualizing one variable, namely the weight variable, which I drag onto the x-axis, and we're ready to go. I could simply delete the title again. So let's do this. And I click OK. And now I see that the histogram is produced. The weight follows a normal distribution as far as we can tell from the histogram. And we see that the mass of the distribution is around 78 to 80 kilograms. So we're fine with this. Now, after using the univariate visualization, we do a bivariate visualization with a scatter plot. So let's do this. I again click on Graphs, Chart Builder, and now I reset the menu and I choose the scatter diagram. I drag and drop this simple diagram, and now I drag height onto the x-axis. That's our dependent variable, and we use weight as the dependent variable, the variable we want to explain, and we plot it on the y-axis. And again, I'm ready to go. I could customize this plot further, but I'm fine with this by now, so I click OK. And here we see the scatter plot of both variables, and we see a clear positive relationship. So it seems rewarding to analyze this further and describing the data or the trend in the data with two coefficients and a linear model. So let's do this. When we want to create a linear model, then our outcome variable, weight, has to be continuous. This is the case. So let's start. I click on Analyze and on Regression and on Linear Regression. Here I now select the dependent variable using drag and drop, and the explaining independent variable is height. This is all I need to construct a linear regression model. So let's click OK and see the result. Here I have now information about the variables, the independent variables used, in this case height. Furthermore, we get a model summary. Here we see the R squared value. This is the explained variance. How much can we explain with height when we want to explain weight? In this case, it is 0.669. And we have something called the adjusted R squared, so the adjusted explained variance. This is the better estimation when we include more than one variable because it accounts for the fact that the explained variable will increase anyway when we include additional independent variables. So to discount for this fact, we compute something called the adjusted R-squared, which is independent of the number of included independent variables. So let's go further. Here we have the so-called Anova table. The Anova compares two models. The null model, which uses no independent variables, which has thus only an intercept, which is the mean value of the y variable. So this null model is compared to our model where we use an independent predictor, in this case height. And the Anova tells us if both models are equal. This is a hypothesis the Anova tests. The null model is equal to our model. And the probability that this hypothesis is true is given by the p-value. This is the p-value, and we see that the p-value is very low. And thus we have to reject the null hypothesis that the null model equals our model. When we reject this hypothesis, we accept the opposite, which is simply that the null model is different from the model with the independent variable, our model. And because the null model is the worst model we can think of, our model predicts the outcome, the dependent variable, better. So we have a valid regression model at our hand. Our model is better than the null model. And the model is always better when at least one predictor is significant. So let's look at the predictor. Here we see the regression table with our two beta regression coefficients. The beta regression coefficients describe the data completely using a linear model. This constant is the intercept, which we can't interpret in this case because there is no meaning for a soccer player that has height 0. But in this case, height is very interesting. That's the beta 1 coefficient. We see the beta coefficient is 0.9, which means that with each unit increase in height, so with each additional centimeter, the player gains on average 0.9 kilograms. You have to be very careful. I said that the player gains weight. On average, the player is heavier by 0.9 kilograms. So there is not necessarily a causal relationship implied. So it's just a relationship. Larger players tend to be heavier. Okay, and now we see that there is something of a t-value and a standard error. And from this we can infer if this beta coefficient is actually 0. If it is, then the slope is 0 and then there is no relationship. But in this case, the height beta coefficient of 0.9 is significantly different from 0. We reject the null hypothesis that beta 1 is 0. Thus, the beta coefficient has to be different from 0, and thus it has a relationship. A significant relationship. So this is basically how we interpret the regression model. But remember, there were assumptions that must hold true when we use a logistic regression model. The first was that the dependent variable weight is continuous. This is the case. The second important assumption is that the relationship between height and weight is linear. And to check this assumption, we use the errors and test if they are normally distributed. If they are, we assume that a linear model is a good model to describe our data. So now we have to display or visualize the errors. How do we get the errors? We have to reconstruct the logistic regression and setting an option. So what do I mean? We click on Analyze, Regression, Linear, and we will see that all the options are stored. Now I request more information. I want the estimated errors. I can request this using the Save button and say that I want the residuals, that are the errors, and the unstandardized errors. So I click Continue, and now when I compute the linear regression model, SPSS will provide the errors, and then we can check if they are normally distributed. So let's do this. I click OK. The model is refit. We get the same result, but now we get an additional information which is stored in the data viewer. So let's go back to the data viewer. And here we see the residuals. That is the deviation from the actual observed data point. So when we use the model to estimate the weight of Ter Stegen, that's a German goalkeeper, then the model was off by 3 kilograms. The model was off 5 kilograms when estimating Manuel Neuer's weight, and so forth. So let's visualize the distribution of the errors. I click on Graphs, Chart Builder. I reset the menu, and now I request a histogram. And I can now click the unstandardized residual. So I use this as the x-axis. And what I can do now is to additionally plot a curve of the normal distribution. So this is a nice feature. I select this option, display normal curve, and I click OK. And now the histogram is computed. And as we can see, this histogram of the errors actually approximates a normal distribution. And so we can assume that the relationship is actually linear. A second way to test this assumption is to construct a QQ plot. So let's do this very quickly. So to visualize the QQ plot, I just click on Analyze, Descriptive Statistics, and there I can select QQ plot. Now I have to simply select my residual variable, and I test it against the normal distribution. Remember, the QQ plot plots the actual quantiles against the expected quantiles under the normal distribution. I could select another distribution, but I want to test if they follow a normal distribution. When they do, then we expect a line on which the points lie. So this is all we have to do. I simply click OK. And now, because we know that this assumption holds true, we see actually that all the lines build a nice chain of dots along this line. So again, we come to the same conclusion. The relationship between weight and height is actually linear. So let's move on to a second interesting example. In this example, we use a categorical variable as the independent variable. Remember, in linear regression models, we can use categorical or continuous variables as the independent variables. The dependent variable, however, y, has to be continuous anyway in linear regression. In this example, we will use the independent categorical variable position goalkeeper, which we see here selected. This is a binary variable with two possible states. The one indicates that the player is actually a goalkeeper, so let's check this. It's Manuel Ter Stegen, and he is actually a goalkeeper. The second soccer player in our data set is Manuel Neuer, and again is a goalkeeper, correctly indicated with a 1. This player is indicated with a 0, and we see that this is Toni Kroos, and he's a field player, so we're fine. 1 indicating a goalkeeper, is 0, a field player. So I can use this information for a linear model to explain or to analyze a potential relationship. Is the position related with the weight? Are goalkeepers perhaps heavier than their outfield counterparts? Let's check this by constructing linear regression. We click on Analyze, Regression, Linear, and now I reset this menu and select the weight variable as the dependent variable, the goalkeeper variable as the independent variable. That's our binary variable. Because I reset the linear regression menu, I have to again specify that I want to save the residuals, the unstandardized residuals. I click OK. They must follow a normal distribution to describe a linear relationship. Furthermore, I use the statistic to request the confidence interval of the regression coefficients. And I click continue, and now I'm ready to go. I click OK, and SPSS will figure out the correct model with the best line for us. So the first table is the information about variables that were entered, in this case position goalkeeper. That's fine, that's what we requested. Here in model summary we get the very nice quantity of the R squared, the explained variance, and the adjusted R squared, which is around 15%. Again, both values are roughly the same when we have few independent variables. When we use multiple regression using multiple independent variables, then we should prefer the adjusted R squared value because it's unbiased or adjusted. The Anova table tells us if our model actually is equal to the null model, as we have learned. In this case, the p-value is very low and we reject the null hypothesis and we assume that our model is better. It's different from the null model. And thus we expect at least one beta coefficient to be significantly different from 0. So let's check this. The constant plays a crucial role in this example. We will discuss that. But let's see position goalkeeper. It's significantly different from 0. We can see that by the confidence interval from 6.8 to 8.9. This confidence interval does not include the neutral value of 0, indicating no relationship. Because it does not include the neutral value, we conclude that there is a potential relationship. So that there is a significant relationship. So when the p-value is less than 5%, then the confidence interval, the 95% confidence interval, will not include the value null. So we can use both quantities to conclude if our regression coefficient is significantly different from 0. So what's the actual value of the beta coefficient? Well, it's roughly 8. So what does this mean? First of all, in this case, the constant actually has an interpretation. Because remember, now when x, our independent value, is 0, this has actually a meaningful interpretation. Because when it's 0, then we assume that the player is a field player. And in this case, the second term with the beta 1 coefficient cancels out completely and we are left with a constant. And the constant then is the average weight of the field players. And now when we change the x variable from 0 to 1, then we multiply the beta coefficient with 1, that's the beta coefficient, and we add it to the intercept. And we can now conclude that goalkeepers recorded with a 1 are on average roughly 8 kilograms heavier than their counterparts on the outfield. So with this regression model, we conclude that the independent variable goalkeeper is actually related with the outcome. So I think this is a nice interpretation, and let's see what about the residuals. Here you see a residual statistics, which is fine, but we don't bother. We just want to construct a histogram to check the normality of the error. So I click on graphs, chart builder, and now I will reset this again, use the simple histogram, and then I use the unstandardized residuals. And I click OK, and now I see that again, I forgot to plot the normal curve. I just visit the menu again, and now I check display normal curve. I click OK, and now I see that this line is actually an approximation. It does not quite follow a normal distribution, but it's a good approximation. We're fine with this because we don't see any pattern in the histogram. It seems to follow a normal distribution, so we say that the assumption of normal distributed errors are met. So this again is a fine linear regression model. What you can do by yourself now is to try to use both variables, height and goalkeeper, as the independent variables and try to figure out and interpret the model, what it actually means.